Hello everyone. Let's start with a simple question. How do we usually understand motion in real life? Think about when you're in a car. You don't just hear the driver say the speed, you see how far you've gone as time passes. Graphs in physics do exactly that. They give us a visual picture of motion. A time displacement graph shows how the position of an object changes with time. With one quick look, you can tell if the body is at rest, moving at constant speed, or accelerating. For instance, a straight line tells us uniform motion, while a curved line tells us velocity is changing. Let's first understand the basics. In these graphs, the horizontal axis, or x-axis, represents time, usually measured in seconds. The vertical axis, or y-axis, represents displacement, usually in meters. Each point on the graph tells us where the object is at a particular instant of time. The most powerful part is this: the slope of the graph gives the velocity of the object. So, the steeper the slope, the faster the object is moving. That's why these graphs are so important in kinematics. Now, let's see the simplest case. What if the body is at rest? Then its displacement does not change at all, no matter how much time passes. On the graph, this appears as a horizontal line parallel to the time axis. Since displacement remains constant, velocity equals delta x by delta t, which is 0. Imagine a book lying on a table. No matter how long we observe it, its position doesn't change. That's exactly what the flat line represents.
Next, uniform motion. In this case, the object covers equal displacements in equal time intervals. On the graph, this shows up as a straight line inclined to the time axis. The slope of this line gives velocity, which remains constant. For example, if a car moves on a highway at 20 meters per second, its displacement time graph will be a neat straight line, rising evenly as time increases. This simple graph tells us that the car's motion is steady and predictable. Now comes the more interesting case, non-uniform motion. Here, displacement does not increase evenly with time. The graph becomes a curve. If the curve bends upward, the object is accelerating. If the curve bends downward, the object is decelerating. Mathematically, the instantaneous velocity is found by drawing a tangent at a point and finding its slope. A good real-world example is a stone dropped from a height. Its displacement grows faster and faster with time, so the graph curves upward. Let's solve a problem to really see how these graphs work. Suppose the displacement of a particle is given by x equals 5t squared, where x is in meters and t in seconds. We want to find the displacement at 2 seconds and the velocity at that instant. Step 1. Substitute t equals 2. X equals 5 times 2 squared, which is 5 times 4, equal to 20 meters. Step 2. To find velocity, we differentiate displacement with respect to time. V equals d by dt of 5t squared, which is 10t. Step 3. At t equals 2, velocity equals 10 times 2, equal to 20 meters per second. So the displacement time graph here would be a parabola, and the slope of the tangent at 2 seconds gives the velocity of 20 meters per second. This shows how graphs connect equations with visual understanding. Let's wrap up with a quick recap. Time displacement graphs give us a simple way to visualize motion. A horizontal line means rest, a straight inclined line means uniform motion, and a curve means non-uniform motion. The slope of the graph gives velocity, and the tangent gives instantaneous velocity. We also saw through an example that mathematical equations like x equals 5t squared directly shape the graph into a parabola. These graphs are not just classroom tools. Scientists, engineers, and even traffic analysts use them to study motion patterns. I hope today's session has made you comfortable with interpreting and analyzing displacement time graphs. In the next lesson, we'll dive deeper into velocity time graphs, which reveal even more about how objects move. See you there?